Welcome everyone. So this is the latest session of the Storms, Eddies and Science kind of monthly, more or less monthly meeting to kind of talk about various work from various of our projects. So there's another meeting next week with another 3 speakers, which I will advertise at the end. But today we have a really interesting and diverse set of talks. So we have first Mulalo talking about storms around South Africa. Then Stephy's going to talk about eddies. So we're doing well with our storms and eddies. And then Martin's going to talk about some disease stuff with the models. So it should be really diverse and interesting. So I suggest the speakers, so the kind of notes for the meeting say around 10 minutes of talk, but I'll definitely stop you at 15, but kind of if you aim for around 10 or 12, and then we definitely need 20 minutes for each speaker to have their questions as well. So Mulalo, the floor is yours.
My name is Mulalo Maphugwi. I'm a PhD candidate, University of Cape Town. I'm working with Dr. Ross Blamey and Professor Chris Wiesen. So today I'm going to talk about mesoscale convective system in Southeastern Africa. So given the time limit and the time constraint is only 10 to 15 minutes, this presentation is going to be more about why this work is important and critical for our region, the methodology that we have followed and used. The sensitivity test results are there. They are done. We have run them the past few days, but we need more time to refine them and make them and analyze them. So the future direction also at the end, I will explain, will also depend on the EERIE simulation that will be coming out. So let's get started. So what are mesoscale convective systems? These are organized thunderstorm clusters that are often defined to have a minimum horizontal extent of precipitating area 100 kilometer and moving in at least one direction. These systems are critical for rainfall as well as distribution of heat and moisture globally. They are associated with strong vertical wind shear as well as damaging winds, flash floods, hail, as well as lightning. So they are very dangerous systems. So in your left, you are seeing a mesoscale convective system that took place in Southeastern Africa in December 2020, on the 23rd, claiming the lives of 3 people as a result of lightning associated with it. In the bottom left, in the bottom right rather, you're looking at mesoscale convective system precipitation annually from Feng et al. 2021, looking at the precipitation per day from systems that are mesoscale convective systems globally. You can see in the tropical region, you tend to have more precipitation associated with these systems. So where are these systems found? As we have already said in the previous slide, the tropical regions are very hotspot for these systems. The black box there showing the continental United States, it's has developed a lot of studies, or a lot of studies have been developed over that region when it comes to mesoscale convective systems. In South America, there's also been quite a few studies that have come out, especially lately, with a lot of projects focusing on mesoscale convective systems, as well as Asia, there in the orange box. In Africa, a lot of studies that have been focused on mesoscale convective systems have also been confined over the Congo Basin as well as West Africa. Southeastern Africa there in the bottom with 2 question marks. I haven't seen a lot of studies, and we tend to have a lot of rainfall also coming from these systems, as well as damages when it comes to lightning associated with it and flash floods due to these systems. The bottom picture, you're looking at precipitation as a result of convection. A lot of regions globally tend to get most of the precipitation as a result of convection, and then mesoscale convective systems are part of that. So you can see Southeastern Africa there where my mouse is pointing. We tend to get also a lot of precipitation as a result of convection, as well as Africa, obviously, West Africa, as well as the Congo Basin is a big one, but similar to mesoscale convective systems numbers, you see continental US, South America, as well as Asia tend to get a high number of those systems, as well as precipitation as a result of convection. So what are the environmental influences of these convection as well as convective mesoscale systems? You could see that most of these systems tend to found in areas that are closer to the tropics, where the SSTs, the surface temperatures, are very, very high. Continental USA, for example, using the South America as well as Asia and West Africa. This is where these systems have been studied and found that they occur mostly, which means that we are looking at the role of warm SST, for example, over the Gulf of Mexico. There's the formation and intensification of these mesoscale convective systems. From previous studies have found that they tend to influence those systems. In South America, order to that, you have on the right there is a topography figure looking at the topography, which actually tends to play a role when it comes to initiation of most of convection and mesoscale convective systems. For instance, in South America, it was found that the Andes Mountain actually tend to play a role when it comes to convective initiation of mesoscale convective systems. So we're looking at global SST, we're also looking at topography in most of the region that actually we found mesoscale convective system as things that actually play a role, but the dynamics of how much and how they intensify, they tend to differ from one region to the next. Southeastern Africa, we also have an interesting climate and an interesting adjacent ocean that actually tends to influence convection as well as mesoscale convective systems. But unlike other regions globally, we haven't seen a lot of studies focused on this region. For example, we don't know you can see the blue arrow there pointing at the Mozambique Channel, where you have high SSTs. Previous studies from Maurin 2022 has found that the Mozambique Channel tends to fuel and then influence convective activity over Southeastern Africa as well as Southern Africa in general. But to what extent and the dynamics is not really understood. The black arrow over there is showing the Agassiz return current, which also tends to influence when it comes to moisture floods and warm SST, the storm tracks over Southeastern Africa and mesoscale convective systems. But to what extent and the dynamics of that, we still not really clear. Also, the red arrow over there is showing the cold Benguela current on the western side, which also tend to suppress rainfall in austral summer months, but also the dynamics of that are actually still not very much understood in Southeastern Africa. So in this study, we are focusing more rather on the convective hotspot of Southeastern Africa, and then investigating mesoscale characteristics, their changes with relation to identify rainfall trends in the region. The first step, obviously, is to build a long-term climatology over Southeastern Africa using long-term observation data, GPM measure, IMH data, as well as R5 data. In the long run, we are going to track and then do what we did on the observation data on the EERIE simulation, with a focus on associated precipitation of mesoscale convective systems, mesoscale characteristics, as well as the influence of the adjacent ocean and the SSTs. So the first thing that we're looking at is mesoscale convective system tracking. As I've already alluded to in previous slides, you can actually see these systems through a brightness temperature, which means that you can see their size, and then they tend to actually move similar to atmospheric rivers, tropical cyclones. This system tend to move, so which means that we can use the size threshold as well as brightness temperature threshold to actually track them. Over the past few years, there's been a number of tracking methodology that have been used in order to track the mesoscale convective systems. One of the tracking programs that have become popular over the past few years as a result of being able to be applied in various data sets is PyFlex Tracker. So here we have used PyFlex Tracker on both observation and will also be applied to models in order to track these mesoscale convective systems. Obviously, a cloud top or a cloud threshold with a certain size and a certain brightness temperature is found in first time step, second time step, third time step in order to be tracked in a either a model as an outgoing long wave radiation or an observation. So the splitting and merging also is one of the things that PyFlex tracker handles and explicitly, but has been a challenge when it comes to these tracking programs. So now we move to the first sensitivity test that we did on this PyFlex tracker. So on the left, you're looking at a storyline that we put out on the EERIE website, I think a few months ago, looking at the storm that took place in 2020, December 23rd and 24th, resulting in the loss of 3 lives. So the first thing was to try and do a run of this system and then see the mesoscale convective storm, try to track it, how it took place. So the second image there, you're looking at the system at a certain time steps, the brightness temperature. And then the third one here is the track location of the track that took place on that single event, resulting from that single event. But I'm going to actually run it on the second slide, then we'll come back to this slide. So here I'm going to give you a simulation of a PyFlex tracker sensitivity test on the day of the case study or the day that that event took place. So on the left here, you are looking at IR brightness temperatures, and then on the right there, you are looking at precipitation that is associated with the PyFlex tracker or associated with the storm rather, using PyFlex tracker. So this is what's interesting about this tracking program, the fact that it combines both brightness temperature as well as precipitation that is associated with the storm. So let's look through and see. So I would like to take your attention and focus on storm tracker number 3, which is one of the main storms that took place on the day. So most of these storms, what happen is that they initiate overland and then they tend to track towards the adjacent ocean on the east. So one of the dynamics that we don't understand is that most of these storms, it's the climatology, when they track from land to the ocean, they tend to intensify and then have a tends to be bigger as much as they enter the ocean. So the dynamics of that is still much not understood, how ocean actually tends to influence, how SST and the ADs actually influence this tracking. So we'll just look through, okay? Yeah. So the numbers represent all the tracks that were found on the day. And then one of the interesting things, like if you look there at the top for at track number 1, you will see that it's a tropical cyclone. So that's one of the issues with the tracking program, is that it just tracks anything that is moving as long as it's fitting the threshold of cloud top as well as rainfall, then it tends to track. So that's one of the things that sensitivity tests are important, because it actually turns what is not a mesoscale convective system. So just going back to the previous slides of track location, you look here, it's all the tracks that we found on the day. On the bottom right there, we found that there was also 2 track number 4 as well as track number 5. That is one that is also like associated with cold fronts as or rather frontal system, rather than not a mesoscale convective systems. But because there was a lot of precipitation associated with that, the program will tend to find it as a mesoscale convective storm. So we still need to do some tweaking and also some configuration when it comes to our track and how it tracks these things.
Mulalo, that's 13 minutes, so just 2 more minutes.
Okay, so just to finish up, so what we're gonna do what we have done is build a sensitivity test. It's a long-term climatology using brightness temperature as well as image rainfall data at 10 kilometers. And then we're gonna switch off the precipitation and do at 10 kilometers, and then error 5 OLR as well as precipitation, as well as switch off the precipitation on ALR. And then the next steps obviously is moving into modeled world, simulating these mesoscale convective systems in general circulation model has been a long-standing challenges. So projects like EERIE and also others actually are providing more, especially in Southeastern Africa, where we haven't really seen any tracking methodology and training program being applied. So here you're looking at a figure as 100-kilometer model. That's how it looks like. And then you're looking at a parameterized storm. So EERIE model is going to come here between storm resolving and parameterizing storm. So we are trying, this project provides an opportunity to enhance our understanding of this mesoscale convective storm, but most importantly, the role of ocean mesoscale on the intensification as well as assisting with future projection of our region. Thank you so much.
It's great. Thank you very much. That was really interesting, which is why, sorry, I was going to give you a warning at 10 minutes, but I was too interested.
Okay. Okay. Thank you. Thank you.
Questions? I'm not completely convinced I can see hands on my WebEx, so shout if it looks like I haven't seen you. I was gonna ask a question unless there's no one else. So you mentioned at the start that with kind of that the MCSs were often associated with places with warmer SSTs. Do we have any idea, as the SSTs get even warmer into the future, is that likely to change the MCSs, make them more of them or stronger, or is that we really don't know that yet?
Yeah, so that's one of the long-standing questions, because high resolution models couldn't really have a good climatology of MCSs, especially in many regions over the world, not just Southeastern Africa. So we couldn't really tell in the future how, if they're going to intensify, if we're going to see a more number of them over different parts of the region. So with high resolution model, not just EERIE, but from other projects as well, we're still starting to see high resolution grants of the future projections. So that's going to tell us if these systems are going to intensify. Also the role of the SST, warmer SST, does it mean it's going to have warmer storm, or is it going to be stronger in terms of intensity?
Okay, great.
Yeah.
That'd be very interesting. Yeah.
Yeah. Okay. Thank you.
Anyone else have a question? Just shout.
Yeah.
No? No questions? Okay, brilliant. Thank you, Mulalo. That's really interesting.
Thank you. Thank you so much.
Okay, next speaker is Stephy. Are you here, Stephy?
Hi, Malcolm.
Hi. Please go ahead.
Thank you, Malcolm, and thanks everyone for joining. So I'm a postdoc at UC Louvain, and I'm working on the mesoscale Eddy-ice interaction in the Arctic and Antarctic, but in today's talk I'll be sharing most of the results from the Southern Ocean. And for this work, I am collaborating with my team in UC Louvain with Hugues, Ting-Shen, and also I've been developing this composite work mainly based on the work from Diane, and also collaborating with her. So first I will jump, I'm working in the working package 5 and 6 for the EERIE project. And in this talk, some of the results that I'll be presenting is relevant to the first 2 points in this objective. So to understand the influence of ocean mesoscale features on the sea ice, the thermodynamic and dynamic processes controlling sea ice mass per jet. So some of those concepts will be discussed today. I'm going to jump straight into some background on the cyclonic and anticyclonic eddies in the Southern Ocean. For that, I'm using the work from Frencher et al. In 2015, and they've done, based on observation, some detailed or extensive survey in the Southern Ocean, looking at the hotspots where a lot of eddy activities happen, how their features are, what sort of properties they have, and so on. So from their work, I'm using this idealized diagram on showing how the cyclones and anticyclones properties are. So in a cyclonic eddy, you have a low sea level anomaly, you have a cold, fresh core, and you have the thermoclines that are upwelling, or you have a shallower core. And in an anticyclonic eddy, you have a positive sea level anomaly, a warm saline core, and the thermoclines are downwelling, or you have a deeper core. But while these studies are quite extensive, they still don't go into the sea ice zone of the Southern Ocean, or the sea ice itself presents a challenge for a lot of observation work, and also some of the instruments going into those regions are limited. And also for satellite altimetry, the sea ice presents limitation in observing eddies in these regions. So we have to rely on a lot of models to study the eddy-ice interaction in the high latitudes. And before I go into eddy-ice interaction, I want to say two main differences that happens when we go into the sea ice zone here in the Southern Ocean. So first one is the temperature inversion. So most of the global ocean, we are familiar to have a warmer surface layer and a cooler ocean interior. But when you go to the high latitude Southern Ocean, where sea ice exists, you have a relatively shallow, cooler and fresher surface layer, and a warmer subsurface layer, usually circumpolar equator. And also you have a seasonal sea ice cover. So sometimes that can be very fragmented ice, or sometimes it can be pack ice. So if it is pack ice, it can actually act as a lid and drain energy from eddies, etc. When it is very fragmented and loose, it can move around with the eddies acting like a tracer. And now with these differences, you have the eddy dynamics that acts in this region, and that can actually cause some different changes from what we regularly consider with the open ocean conditions. So there are some studies that have worked on it, sometimes idealized studies or using regional settings or 3D channel models, etc. So here I'm showing the results, showing the concept from Gupta et al. On the eddy ice pumping mechanism. So what they find is that when you have a very thick pack of ice, which is immobile, a large pack, it can exert a drag on the ocean surface, opposing the eddy motion underneath. And because of this resistance or this drag, it can give rise to Ekman velocities. So in a cyclonic eddies, the Ekman velocity would result in Ekman pumping, so the downwelling, while in the anticyclone, it can produce Ekman suction or upwelling. And as I said before, when you have a cooler surface layer and a subsurface warmer layer, due to the Ekman pumping, it shields the sea ice from the warmer waters in the cyclonic eddies, which can actually lead to more sea ice growth. And in the anticyclone, the warmer water comes closer to the sea ice and can cause melting. So this is the more theoretical or idealized results. And now we try to see how that shows up in the EERIE models. So I'm using the spin up from the IFS FESOM and ICON that's available in the GrantAgreement. And from both of them, I used the first 2-year daily data for this composite results that I'm showing today. And we do the composite with a lot of steps, and we are actually calculating the composite after getting the anomaly from the climatology, which makes it easier to compare between the models. So I'm comparing the results from IFS FESOM here against the theoretical concepts. So here we have the sea surface temperature at the core of a cyclonic and anticyclonic eddy in the open ocean, and also looking at that in the sea ice zone. So you have it consistent with the theory, a cooler core for the cyclonic and a warmer core for the anticyclonic. And that signal is a lot stronger in the open ocean compared to the sea ice zone. And then when we look at the sea ice thickness, you have a positive signal that is more ice forming in the cyclonic eddy and a little bit of melt in the anticyclonic eddy. So when we look at that, that is consistent with what the theoretical study has predicted. So in a cyclonic eddy, you have ice growth and a cooler anomaly, and the anticyclonic the opposite. While this is true, I have done this assessment for the composites averaged over the entire year, and what I'm showing here as sea ice is the regions with sea ice concentration more than 70%. But when we look at the Southern Ocean, there is different categories of ice regions. So regions with very thick pack ice, the marginal ice zone where the sea ice concentration is a lot less, and then regions in between. So I wanted to check if all of these concepts can be generalized for all of that, or if there's going to be any differences. So to do that, we separate the sea ice zone into 4 categories. So the almost open ocean region where the sea ice thickness is 10% or less. The marginalized zone north where the sea ice thickness is between 10 and 40%. The marginalized zone south where the sea ice concentration is between 40 and 70%. And then the ice zone where the sea ice concentration is 70% and higher. So this categorization is similar to what was done by Auger in their observational study. So we have something to compare. And so now when we look at the composite results for the different ice category, I'm doing something to simplify it. So instead of showing 48 composite plots, I'm just showing the average at the core. So the core properties are averaged at half eddy radius for the whole results. And then I'm just showing the line plots from hereafter just for simplicity. So with that, in the FESOM, I'm showing the results of sea surface temperature at the eddy core between the different ice categories. So moving from open ocean into pack ice. So open ocean or no ice, marginal ice on north, marginal ice on south, and the ice category. So you have a strong signal or the magnitude of the signal is much stronger in the open ocean region, and then it reduces as you go into the ice zone. And then for icon, you see something similar, but then the anticyclone seems to be a lot more negative in the icon simulation. When we look at the sea ice concentration at the eddy core, both models seems to be having a similar sort of distribution influence, and the values are of similar range. So in both FESOM and icon, this seems to be more consistent. But however, when we look at the sea ice temperature, they are quite different. So in the FESOM model, the kind of changes that happen from the open ocean towards the ice category at the eddy core is comparable between the sea ice concentration and sea ice thickness. So something similar is happening there. Whereas in the icon model, the sea ice thickness is producing quite an anomalous kind of response. So we have to still look into what's going on there. So here I was saying whether we can generalize the eddy-ice interaction across different ice categories. So is it going to be melting in the anticyclone everywhere or freezing in the cyclones everywhere? But when we think about this sea ice region, it has a strong seasonal evolution. So in winter, it has a large area and according to observations, approximately 18 million square kilometers of ocean area is covered by sea ice, and then it melts to about 3 million square kilometers. And also a lot of changes occur in the upper ocean as well, in terms of stratification, cooling, warming, mid-layer depth, so on. So I wanted to see if these kind of changes can have an impact on the Eddy-ice interaction as well. So I tried to look at the evolution at monthly timescales. If I'm going too fast, or if you have any doubt, you can stop me and ask questions. And so here I'm doing a sanity check with sea surface height and also trying to explain what the figure is like. So we have the ice zone that is 70% and higher sea ice concentration, marginal ice zone in green, and the marginal ice zone north in red. And the cyclonic eddies are the solid line, and the anticyclonic eddies are the dotted or dashed line. And so when we look between
Steffi, that's 12 minutes. Okay.
Yeah.
Got 3 minutes left.
Thank you. So when we look between the FESOM and ICON model, there seems to be some, changes in the seasonal signal in the eddy interaction, but you can also think about it as in the summer, the sea ice, if present in the model, is in a much higher latitude with less energetic eddies or smaller eddies. And then as the sea ice expands, it's moving into the region with the larger eddies or high energetic eddies. So that could be reflected in this. But anyhow, we look at the different properties in the seasonal evolution as well. So for FESOM, the SST, again, similar to the sea surface height changes that we saw, it also has some interesting changes with the magnitude of the eddy core properties along the seasonal changes. And when we look at ICON, we don't really see a similar pattern. Instead, most of the anticyclones are in a cooler temperature signal. So I did a sanity check by including the open ocean conditions. So when you include the open ocean, they do actually have the change in polarity, but in the sea ice zone, ICON is not producing that warm versus cool anomaly in the eddy core. And when we look at the sea ice concentration, there seems to be some similarity between the two models, but still in ICON, the polarity change between cyclonic and anticyclonic is not as robust as you see in FESOM. And finally, when we look at sea ice thickness, it's really hard to compare between FESOM and ICON model. And in the FESOM model, the melt happening in summer seems to be a much stronger signal. And during the rest of the year, it is kind of consistent with the theory with the melt in anticyclone and freeze in the cyclone. However, in the ICON model, the changes are a lot more varying and maybe a bit chaotic. So I still need to look into why it is so different in the ICON model. So that's some of the results that we have right now, and I will go to conclusion. So when we look at the mean effect of the Eddy-ice interaction, that is the total averaged over the entire period, they are quite consistent with the theoretical studies, especially in FESOM, and for many of the variables in ICON as well. And the Eddy-ice interaction does have variability depending on the sea ice category or the concentration of sea ice above the eddies, as well as with the season. But we still have to do a lot more work with other models from EERIE and also further analysis to try and understand the processes. Thank you.
Thank you very much. That was very interesting. Thank you. So, questions? Again, shout if you have a question, because I'm not sure I see hands. So if no one chats, so Steffi, do you have an idea of how significant the eddy process is in kind of helping sea ice formation compared to the presumably the much bigger fluxes and things? Is this a really small impact, or could it be quite a sizable impact on the ice?
So there was a study by Pierre Vanson here, and I think in their study they did do the eddy process versus not having the eddy process, and I think what they found is the eddies impact mainly in the melting of the sea ice. I believe mostly in the marginalized zone, and also because of the and also the transport. So overall, but there was a regional model, and they are finding, if my memory is right, is that the freshwater fluxes had a change in the overall, because the eddies weren't bringing sea ice towards the north and melting as much, but the overall ice volume was not affected a lot by whether or not it was that was their study, but it was not a global, so we still have to look at
Yeah, so it's difficult to tell. Yeah. Okay. Thank you.
Yeah.
Any other questions? No. Okay. So thank you very much, Steffi. So next week we will hear from Amanda about the mean state of the North Atlantic in some eddy-rich models. We'll hear from Benoit about the contribution of eddy variability to sea level changes, and Michael will talk us about AMOC in different resolutions of the HADGEM3 GC5 model. So we have that to look forward to next week. We'll wrap it up there. Thank you, Mulalo and Steffi, very much. I think they were really interesting talks. And I think the idea of these talks, we've got some next week and we've got some in the online GA, is just to get a really nice overview of all of the exciting work going on in EERIE. And then we can talk a little bit about that at the online GA, but then the idea is that everyone will have a good overview of the whole project by the time of our in-person GA in Zurich. And so we can really talk to each other and figure out what we've done and where the exciting opportunities might be kind of over the next 2 years. So brilliant. Thank you both very much. Thank you all for coming, and see you next week.